Supermassive black holes. The engines that power our universe.
Supermassive black holes are one of the major players in the evolution of galaxies.
With no supermassive black holes, you have no Milky Way galaxy, no sun, no Earth, no you.
They're the driving force at the heart of nearly every galaxy in the cosmos.
They're the most monstrous and scary and bizarre aspects of our world, which just fascinates me.
Now, a new mystery has emerged about the oldest supermassive black holes.
We see supermassive black holes in the very early universe, and we don't understand how they grew so large so quickly.
We have clues about their formation, but can we solve the mystery of this supermassive growth spurt? In 2017, scientists gazing deep into the distant universe discover something completely unexpected. A vast supermassive black hole dating from the earliest days of the universe.
This was 690 million years after the Big Bang. The universe was about 5 or 6% of the age that it is now.
Finding a supermassive black hole in the early universe is like finding an NFL defensive lineman playing in Pee Wee football. Something that big shouldn't exist that young.
The supermassive black hole wasn't just super early, it was super big. 800 million times the mass of our sun.
In just a few 100 million years, the universe has somehow been able to collapse nearly 1 billion suns worth of material into a giant black hole. And we honestly just don't know how that's possible.
We measure black holes by the mass of our sun, solar masses. Regular or stellar black holes are a few to 100 solar masses. Supermassive black holes weigh from 100,000 to billions of suns. And scientists have now found over 100 of these monsters in the early universe.
We were shocked to find even one of them existing so early after the Big Bang. It was kind of freakish, to be honest. But then to find that there's whole populations of these things that exist and are well in place at the earliest times that we can look at was truly shocking.
We believe supermassive black holes might help explain the evolution and the destiny of the universe. Astronomers are striving to understand them.
Understanding the origin of supermassive black holes and how they could form so early in the universe's history is something that would change all of astronomy and astrophysics.
How do you get something that massive to form in such a short amount of time?
It's a big question. To begin to answer it, we have to start small by asking how regular stellar black holes form.
Black holes form through the collapse of stars. Everyone knows that. You have a big enough star and it'll collapse to form a black hole.
A really massive star dies in a violent supernova explosion, and if they have sufficient mass, what's left over collapses into a black hole.
The bigger the star was, the bigger the black hole is to start with.
Were the stars of the early universe big enough to collapse into supermassive black holes?
The very early universe was much different than the universe you see around us today. It was filled entirely with hydrogen and helium gas.
This gas amassed into giant clouds, which collapsed under their own gravity. Nuclear fusion ignited the dense cores, and the first stars were born.
Now, we think that these earliest clouds of gas probably made bigger stars than clouds of gas do in our local or today's universe.
It was possible to get huge, giant stars that we call population 3 stars that were just utterly massive.
Population 3 stars are the oldest category of star. Like stellar dinosaurs, they dominated the universe a long time ago. Now, they're extinct.
They'd be weird stars. They would be incredibly bright in the ultraviolet and have very unique signatures that are very different from stars today. But precisely because they're so big and so bright, they would be very short-lived.
These first stars lived fast and died young, exploding in supernovas, leaving behind black holes. But were they supermassive black holes?
When a star blows up, when it goes supernova, most of the mass is ejected away. It just goes flying out, leaving a dense neutron star or perhaps a black hole, but it won't have much mass because most of that mass was blown away.
Even though population 3 stars in the infant universe were very large, they weren't big enough to leave a supermassive black hole behind when they exploded.
Perhaps if we can skip the supernova step, that might be one pathway to understanding how supermassive black holes formed.
Could a dying star's entire mass collapse into a black hole? A clue may lie in a galaxy nicknamed the Fireworks Galaxy.
The Fireworks Galaxy has that flashy name because when you look at it, there are all these supernova explosions going off and making quite a show.
Recently, astronomers were keeping an eye on one extremely bright star in the Fireworks Galaxy.
This star is exactly the kind that we know explodes as a supernova. Astronomers expected it to explode, but then it did something even weirder.
Astronomy is so wonderful because sometimes you see things right in front of your eyes that you can't explain. We saw an entire star just disappear.
In 2007, the star looked like this. By 2015, it had completely vanished. There was no flare or debris from a supernova explosion.
So what the heck is going on?
It turns out that not every massive star blows up with all the fireworks of a normal supernova. You can get what's called a failed supernova.
A supernova fails when the shock wave generated inside a collapsing star can't escape.
In some cases, when the star is very massive, the shockwave never has a chance to get all the way out of the star by the time the star itself collapses into a black hole. Then you have a failed supernova.
The Fireworks Galaxy star may have been massive enough to smother its own explosion before collapsing to form a black hole.
Everything collapses into the black hole. You can actually have a black hole with all the mass of the original star.
Back in the early universe, could the enormous population 3 stars have died as failed supernovas, leaving behind supermassive black holes?
These population 3 stars don't seem to me to be a good contender for the precursor to supermassive black holes. They just would not have enough mass.
Even the most massive stars are only a couple of hundred times more massive than our sun, whereas a supermassive black hole is millions or billions of times the mass of our sun.
Early supermassive black holes can't have formed from collapsing stars. Even giant stars aren't massive enough. So is there some other path to being supermassive? Were stellar black holes cosmic bodybuilders on a fast-track bulking program? We ruled out the idea that they were created from the collapse of very large stars. Maybe they started out as smaller stellar mass black holes and grew to be supermassive by eating.
Black holes are not fussy eaters. They'll consume anything that comes in their path. You know, gas, planets, stars, it doesn't matter. And everything that they consume adds mass to the black hole.
We've spotted a stellar mass black hole currently eating in our Milky Way galaxy. 15 times the mass of the Sun, Cygnus X1 is steadily feeding off the material that swirls around it.
Some black holes are fed through things called accretion disks. It's kind of like the rings around Saturn. There's this thick or thin disk of material around the black hole that feeds it.
Cygnus X1's accretion disk gets constant refills from a nearby source. A vast star, 20 times the mass of the Sun, called a blue supergiant. The black hole has been feeding on gas from this star for about 5 million years.
So if you ask how do black holes eat or consume gas, the answer is gravity. These are very massive objects, and anything that comes within their sphere of influence can be consumed by the black hole.
The more mass a black hole gains, the greater its gravity, and the more food it attracts.
A black hole growing is a little bit like a snowball rolling down a hill. The bigger the snowball gets, the more snow it can accumulate, and so the bigger it gets. It's a runaway effect.
But even if Cygnus X1 follows this runaway growth trajectory, it still may never reach supermassive status. The black holes of the early universe must have fed at a much faster rate.
The biggest issue is, how do you have enough time in the early universe to go from a small black hole that's born from a star to something that's supermassive?
GRS 1915 is another stellar mass black hole. It's a greedy eater, accreting at up to 40 times the rate of Cygnus X1. And when something gobbles food that quickly, it can begin to overheat.
The black hole is accreting a lot of material, and as it's eating, the accretion disk really heats up to very high temperatures. And at those high temperatures, you can get a lot of light coming out of the system.
So the more material that a black hole eats and swallows, the brighter it shines.
This stellar black hole sometimes eats so much, so quickly, its accretion disk pushes out radiation almost 1 million times brighter than our sun. But this brightness has a serious consequence. It stops the black hole from eating and growing larger.
If you wanted me to gain as much mass as possible, as quickly as possible, you would just keep feeding me hamburgers nonstop or whatever. But black holes have a problem that when they eat a lot, they tend to just gobble up a lot of the food in their neighborhood, and then also they start shining out so much stuff that it pushes away much of the food.
The brightness, or luminosity, gets so intense it pushes away incoming material, a sort of safety valve called the Eddington limit.
So in many ways, the Eddington rate could be a kind of a speed limit for the growth of black holes. It could be a governor that prevents black holes from growing even faster by just dumping more and more gas onto it. Eventually, you're going to hit that Eddington limit, and that more gas that you're dumping on won't actually reach the black hole.
This cosmic method of portion control means that stellar black holes in the early universe couldn't have gained weight fast enough to become supermassive.
Black holes need time to grow. They need to feed, they need to eat. Maybe you need to skip a few steps. Maybe you need to start at a medium size or bigger in order to get to supermassive by the time we observe it.
So was there another type of black hole in the early universe? Something big enough to grow supermassive in the time available? In 2017, astronomers studied a dense star cluster called 47 Tucanae on the outskirts of our own galaxy. They detected 25 pulsars, bodies that spin and emit radiation like cosmic lighthouses.
These pulsars are all orbiting a central object. And even though we couldn't see the central object itself, we could watch the behavior and the orbits of all these pulsars around it, and we could figure out how big that central object was.
Well, when you do the math, you come up with something that is about 1,500 to 2,000 times the mass of the Sun. That's actually hidden in the heart of that globular cluster.
So what is the invisible object?
Whatever's lurking at the center of 47 Tucanae has to be big, and it has to be black.
Astronomers think it's a large black hole. At 1,500 times the mass of the Sun, The object is much bigger than a regular stellar black hole, but too small to be supermassive. Could it be what's known as an intermediate mass black hole?
It's extremely hard to find any of these intermediate mass black holes.
This rare category of black hole ranges between 100 and 100,000 solar masses. At that size, they may have been large enough to become supermassive very quickly.
Intermediate mass black holes could be what gives supermassive black holes a head start in life.
Astronomers search for intermediate mass black holes. They may have been large enough to act as seeds for the first supermassive black holes. Yet so far, they've escaped discovery.
They're like the missing link, and I mean that for real. They're missing.
Imagine you're an alien who's arrived on the planet Earth, and you know very little about the human species. And when you look around, you only notice tiny, tiny little children and grown adults. You don't see any adolescents, right? And intrinsically, you know that the tiny little children grow up to be full-size adults, but you don't see how they got there, right? You don't see the intermediate stages of growth. That would be really, really weird, right? That is the case for supermassive black holes. So it's like a universe without teenagers.
Or that's how it looked until September 2020. Scientists studying gravitational waves picked up the signal of an extreme event in the distant universe.
What researchers are looking for are things called gravitational waves. They're like ripples in space itself. Most signals sound a little bit like a chirp. It's a noise that's very characteristic. It goes a bit like sort of whoop. But this particular event was so extreme and so sudden, it just sounded more like a thud.
This faint thud from halfway across the universe is music to the ears of intermediate black hole hunters. Because its pitch can mean only one thing.
This could only have been created by two really massive black holes colliding into each other and producing a combined black hole with a mass that's 142 times the mass of our sun. So that is, for the first time, getting into this intermediate mass black hole regime.
This is the first confirmed observation of an intermediate black hole.
Finding direct evidence like this for an intermediate mass black hole is absolutely fantastic.
Now that we're certain intermediate black holes exist, could they help explain the origin of supermassive black holes in the early universe?
These intermediate black holes really could be the first seeds of the supermassive black holes. You would need something like that to form really big, really early, to even begin to explain these very massive, supermassive black holes that have formed just a short time after the Big Bang.
How do intermediate black holes form in the first place? The recently discovered one came from the collision of two smaller black holes. They may also form in giant clouds of gas.
It could be that in the earlier universe, you can just have large clouds of gas that can lose enough energy quickly enough to just spontaneously collapse and form a black hole of this size.
The enormous cloud of gas contracts and gets denser and denser, the way it would if it was starting to form stars, but it's somehow able to remain coherent and collapse into one giant object that forms an intermediate mass black hole.
A giant gas cloud undergoing a direct collapse down to an intermediate mass black hole would be a rare sight.
You think it would go giant cloud, slowly collapsing black hole. But instead, it's more like giant cloud, black hole.
So one day you see this massive gas complex, and then you blink, and it's collapsed, and now you're face to face with a big black hole.
At least, that's the theory.
Getting a black hole to form from the direct collapse of a gas cloud is very tricky.
Gas clouds tend to split up and collapse into a multitude of stars. collapsing into one object would take unique conditions. One possible scenario involves two neighboring galaxies. The first, a young proto-galaxy, a gas cloud yet to form stars. Next door sits a larger galaxy. It's forming so many stars, radiation is bursting out all over its young neighbor.
Because they're in close proximity, the energy from the large galaxy prevents the smaller galaxy from forming its stars. So that means that it'll continue to collapse in cloud form before moving to star formation.
The gas cloud becomes large and dense enough that gravity eventually pulls it in on itself. When it can't ignite into stars, the collapse creates an intermediate mass black hole.
I think this idea is very intriguing. I don't know if it's physically possible, but then again, there's a lot we don't know about the early universe.
2017. Scientists simulated another way that intermediate mass black holes might form in the infant universe under the influence of dark matter.
Dark matter was absolutely critical for the evolution of structure in the early universe. Without dark matter, there would be virtually nothing.
Dark matter is mysterious. We know it has a gravitational pull on ordinary matter. One idea is that it helped form very large stars in the early universe, stars that later collapsed into intermediate mass black holes.
The idea is something like this. About 100 million years after the Big Bang, dark matter, which dominated the gravitational early universe, was forming big clumps. Then there might have been these supersonic streams of regular matter after the Big Bang, and they were directed into these gravitational cores where dark matter was gathering everything together.
When scientists simulated this, they found that dark matter's strong gravity could pull in huge clouds of gas.
You could actually accumulate as much as, say, 34,000 times the mass of the sun into one gigantic star-like object. That's big enough it would just collapse into a black hole.
A black hole of 34,000 solar masses would sit squarely in the intermediate mass category. It would be large enough to potentially become a supermassive black hole.
It's possible that dark matter directing streams of gas together about 100 million years after the Big Bang was the seed for these supermassive black holes.
Whichever way intermediate mass black holes form, they seem like a good way to start explaining supermassive black holes in the early universe.
The question is then, how do they grow? How do you start from this seed and end up, with something that's 1 billion times the mass of the sun?
Maybe early intermediate mass black holes had enormous appetites, gorging themselves to a supermassive state, feeding on the biggest meals our universe can serve up. Astronomers want to know how the earliest supermassive black holes got so big so quickly. Could they have started as intermediate mass black holes that devoured supersized meals?
It's possible that these intermediate mass black holes could form in an exceptionally rare environment where it can accrete new material at an enormously high rate.
So far, we only have direct evidence of one intermediate mass black hole, and we can't yet detect how it eats and grows. But we could look at much larger black holes for clues. In 2019, astronomers searched for supermassive black holes that are actively feeding. They pinpointed 12 quasars from the beginning of the cosmos.
Quasars are among the brightest objects we know of in the universe, and they're what happens when a supermassive black hole at the center of a galaxy is swallowing up gas and dust, and that generates a tremendous amount of energy and luminosity that we can see.
Surrounding these early galaxies are enormous gas reservoirs called hydrogen halos.
This is great because that acts as fuel for those supermassive black holes. Cold gas can stream into those black holes and feed them.
These huge halos of cold gas are also the building blocks of stars.
These enormous, pristine halos of hydrogen around early galaxies, they're going to be reservoirs to power star formation.
Star formation is a violent process that can create turbulence in a galaxy.
That turbulence makes the gas fall toward the black hole, and then that makes the black hole even bigger.
Hydrogen halos might have spoon-fed early supermassive black holes. This process may have also helped intermediate mass black holes grow quickly. Could the largest black holes show us other, more drastic ways to put on weight? In October 2019, astronomers used telescopes to explore a remarkably clear galaxy called M77.
Because this galaxy is so near to us, we can study its central engine in really exquisite detail at very, very fine resolution.
Not only do you see the bright core, the bright nucleus, but you can see spiral arms, you can see structures in the galaxy, you can see how the whole galaxy is arranged.
When we examined M77's central supermassive black hole, we saw something extraordinary. Its food was coming not from one, but two accretion disks spinning in opposite directions.
Normally around a black hole, all of the gas is spinning in roughly the same direction, and that creates kind of a slow infall of gas and slow feeding. Here we've got a case where some of it's going one way, the other's going the other way. This is very unstable and can create opportunities for lots of gas to get gobbled up by that black hole.
The material in the disks is one enormous, ready-to-eat meal. But dinner will not be served until the outer disk slows down.
If there's a black hole at the center of a galaxy and you're orbiting around it fast enough to maintain your orbit, you're never going to fall in. You're just going to orbit forever, and you're just going to spin around, just like the way the Earth is going around the sun. What needs to happen if you want to fall in is to slow down your speed.
The outer accretion disk will gradually slow down and orbit more tightly against the inner disk. Dangerous collisions of the counter-rotating material will start to occur.
The double accretion disk is like drinking from two soda fountains at the same time. It's great while it lasts, but you're building up some serious gas that is just gonna blow the whole thing away.
In just a few 100,000 years, the double disks will catastrophically collide, and their entire contents will fall into the central supermassive black hole. It will devour everything in one gulp, generating a colossal cosmic burp. In February of 2020, in the Ophiuchus galaxy cluster, we saw the damage a cosmic burp can do.
The Ophiuchus galaxy cluster is a collection of a huge number of galaxies all bound together by gravity. And there's gas in between these galaxies. And when astronomers looked at that gas in detail, what they found was a huge arcing structure in it that they realized was the edge of a cavity.
There's a massive hole in the gas that is over 15 times bigger than the entire Milky Way galaxy. Something frightening had to happen to carve this void out.
The size of this bubble is kind of stomping my brain. We are talking about a hole in this gas that is over 1 million light years wide.
The burp that created this cavity must have been astoundingly powerful.
There are a lot of ideas about this, but there's only one that really can explain it, and that's a supermassive black hole.
A supermassive black hole that suddenly got very greedy.
In order to drive an energetic event like this, the black hole needs to eat. Not just one meal, it needs to eat thousands of meals at the exact same time. It needs to go to an all-you-can-eat intergalactic buffet.
Sometime in the distant past, this black hole must have had a huge episode of just gorging on material falling in. that got super hot, blew out a tremendous amount of material in jets, beams that shot out from the poles of the disk, and that's what basically pushed its way out of that gas, forming this enormous cavity.
The colossal cosmic burp pushed food far away from the supermassive black hole, ending its all-you-can-eat binge and stopping its growth. If an intermediate mass black hole was this greedy, it would come to a similar end. It's no way to gain weight and become supermassive.
This is probably not the way the earliest supermassive black holes grew to such enormous size.
Is there another way supermassive black holes could have formed in the early universe without having to overeat? Maybe black holes smash their way to being giant-sized. November 2018. Astronomers scanning hundreds of nearby galaxies in infrared light spot something extraordinary. Some galaxies had not one supermassive black hole, but two. Are these pairs a clue to how supermassive black holes in the infant universe got so big, so fast?
Seeing these infrared images showing pairs of supermassive black holes at the centers of galaxies and showing that this could be very common just is mind-blowing to me.
The reason we see pairs of supermassive black holes is because two galaxies merge together.
In our picture of how the universe works, galaxies start off as smaller galaxies and grow by merging with other galaxies. So they'll be whooshing around each other and tearing each other up. It's actually quite violent.
When galaxies merge, we think their central supermassive black holes also merge, smashing into each other and combining to build a larger black hole.
Galaxy-scale mergers can be one of the most efficient growth mechanisms for supermassive black holes.
Maybe in the early universe, black holes of stellar or intermediate mass merged repeatedly, getting heavier and heavier until they became supermassive.
We don't really know how common supermassive black hole mergers were in the early universe, but we think they were more common than they are today because galaxies were closer together.
It would have taken millions of mergers to build up the largest supermassive black holes we see today, which could have been a tall order. If that many mergers did take place, then something else seems strange. The black holes we find in the universe are almost all stellar mass or supermassive.
You would imagine that if supermassive black holes form from smaller black holes coming together, then you'd find black holes with masses that range from the smallest to the largest. But we don't. We don't see intermediate mass black holes. My question is, where are the 10,000 solar mass and the 1,000 solar mass black holes?
There's another problem too.
We've never witnessed a supermassive black hole merger in the act. We've seen supermassive black holes on their way to merging, and we've seen ones that we think had gone through mergers, but we haven't caught one in the moment.
As supermassive black holes start merging, they spiral around each other, getting faster and faster the closer they get. But for them to finally merge together into a single black hole, they need to lose what astronomers call orbital energy.
The merger of supermassive black holes means that their orbits have to decay for them to get closer and closer together. So in order for an orbit to decay, that orbital energy has to go somewhere.
To lose energy, the merging supermassive black holes start disrupting the orbits of nearby stars, throwing them off their paths.
So something small and puny that weighs just one sun, like our own star, will often get in the path of these two and just get rocketed out, potentially unbound and flung out of the galaxy entirely.
Each time the supermassive black holes fling out a star, they lose more orbital energy. They get closer and closer.
But eventually, they kicked out all the stars. There's nothing left.
The merger stalls. Like two sweethearts at a high school prom. The supermassive black holes dance as close as they can, but physical contact is not allowed.
So these two black holes could end up spiraling around each other for billions and billions of years.
This is called the final parsec problem.
In 1980, there was a famous paper which addressed this issue that supermassive black holes can only get to within about 1 parsec, or 3 light years of each other, before they can't merge or they stall.
We believe that supermassive black holes must merge. We know that galaxies merge, and so if the black holes didn't merge, we'd see lots of black holes floating around, and we don't. There's always one in the middle. So how do they merge?
Scientists are also investigating invisible forces at the beginning of the universe. Did something we can't see boost the size of the first supermassive black holes? One of the greatest mysteries in cosmology is how the first supermassive black holes got so large so quickly. We suspect mergers could help explain their size. And we know all types of black holes can grow by feeding. But we need more clues.
There's still so much we don't know about the early universe.
The further out we look in the universe, the less familiar the universe becomes. And so the more and more interesting and new physics you need to involve in order to explain these very strange observations.
The puzzle of fast-growing supermassive black holes in the infant universe now takes physicists somewhere new, to the little understood realm of magnetic fields.
The thing about magnetic fields is they're hard. They're hard to calculate, they're hard to understand. They're sort of the elephant in the room for astronomers. We know they're there, but we'd really rather not talk about them.
It's only recently that people are incorporating magnetic fields into their models of galaxy formation, and therefore, maybe it's under the influence of these fields that somehow these supermassive black holes are formed.
To investigate how magnetic fields influenced early supermassive black holes, we must look back at the very beginning. Soon after the Big Bang, the first particles form, cool, and become electrically charged.
Things were very different, radically different than they are now. Particles were whizzing by each other, everything was charged. It was just a very different landscape.
There are no stars yet, not even atoms. But some scientists think moving, charged particles created the first magnetic fields.
Magnetic fields were essentially everywhere in the early universe.
Those magnetic fields would have extended extremely large distances, like a very finely spun web, all through the early universe.
Gradually, atoms form and gather into clouds of gas. These will become the first galaxies, and they're supermassive black holes. During this time, magnetic fields change. They bunch together around the forming galaxies, but we don't know how.
The thing with magnetic fields is they're extremely hard to predict, and you need to do really hard calculations that even now we're only just starting to do.
2017. Scientists design a groundbreaking computer model that simulates patterns of magnetism developing over time. The images show lines of magnetic force getting stronger and more focused across a vast region of space. Some astronomers think these emerging magnetic field lines help shape early galaxies and the supermassive black holes at their cores.
Magnetic fields have this ability to push material around. So one possibility is they could actually help push or funnel material in towards a growing black hole and help it grow faster than it would do otherwise.
In today's universe, we know magnetic fields around planets can deflect dust particles. On much larger scales, matter may also have been channeled into the centers of galaxies of the early universe.
Were the magnetic fields of these early galaxies a conduit that you could get matter dumped more and more into the middle and maybe build up a really big black hole?
Scientists are just starting to figure out the effects of magnetism at the beginning of the universe. But it could have been one of several mechanisms that influenced the size of early supermassive black holes.
We have lots of ideas for how you might be able to form supermassive black holes, but until we see actual mechanisms in action, we just can't really say which of them are the most important routes.
Maybe some other mechanism we haven't even thought of explains how the early supermassive black holes got so big so fast. Hopefully, one day, these monsters of the cosmos will reveal their secrets to us.
Supermassive black hole research is utterly mind-blowing to me. I mean, this is so cool.
It's important to explain how these early supermassive black holes formed in order to have a really concrete understanding of how the universe works.
Supermassive black holes are the great engines of cosmic change. They're enormous points of matter, and because they're just so massive, they can sculpt the evolution of galaxies.
They're the master key to most of the unsolved mysteries in physics.
We have a chance here to understand supermassive black holes so that we can understand the formation of galaxies, the generation of stars like our sun, and maybe even the appearance of life.